So the last type of circuit that we'll deal with in Intro to Engineering is the series parallel resistive circuit. So the good news is there's nothing new. If you apply everything you know about series circuits, current being constant, voltages being additive, Kirchoff's voltage law, everything you know about parallel circuits, voltage being constant, and currents being additive, Kirchoff's current law. We take that and we apply those to the sections of the circuit that are series and are parallel. So here's an example that we'll walk through together. So if you could use my visual of the electron car as we used before, right? So if we start at the source, we come up here, and you notice that there's only one path to go, so we know that this is a series element. As we hit this node here, you notice there's now two paths, so we have some parallel elements. These two, only one way through, so those two are series. And then we come down to this node here, and it splits, and we have two paths for current to flow, which then come back together and go back into the source. So the place to start, students always love to pick up their calculator and start pushing buttons. That's not the place to start with a series parallel circuit. The very first thing to do is figure out how these resistors are connected together. So we have kind of three sections here, right? So this R1 is in series with this series parallel combination, and that in the R1 is in series with this parallel, strictly parallel combination down here at the bottom. So if we were to write that in an equation, here's what it would look like. Right? Total resistance is equal to R1 plus its series, right? These two lines indicate parallel as shorthand. And you know the longhand way to do that is either product over the sums or the sum of the reciprocals, the reciprocal of the sum of the reciprocals. So here's that second section, right? That's this series parallel section right here. So we see that R2 and R3 are in series, and that combination is in parallel with R4. And then the last part here is that purely parallel combination. R5 and R6 are purely in parallel with each other. So start with identifying how the resistors are connected together. Still don't pick up your calculator. What I want you to do next is I want you to write down every relationship between voltages and currents that you can find in this particular circuit. So current-wise, right, the total current goes through IR1, right? Resistor 1 is in series with the source, so it has no other place to go. It hits this junction here where the current splits, right? Some current goes here, some current goes here. So at that junction, we apply Kirchoff's current law. R2 plus R4 is equal to the total. Right? And then comes back together, hits this last junction. So you can see I5 plus I6 is equal to the total. Right, we can also say IR2 and IR3 are the same because they are series elements. What can we say about voltages? Well, straight off, right, R5 and R6, remember those are our two parallel resistors at the bottom. The voltage is the same across them. The next two equations that I have written here are based upon Kirchoff's voltage law. So VR1 plus VR4 plus VR6 is equal to Vs. Right, that's Kirchoff around this outer loop, right? Source plus VR1 plus VR4 plus VR6 is equal to the source. You could write some other combinations, but really that one's fine, right? And then the absolute last thing I wrote is a Kirchoff around that series parallel combination. So VR4 is equal to VR2 plus VR3. Once you have these equations written, everything you can think of about voltage and current and those relationships and the total resistance, then you start to pick up your calculator and start to do calculations. So how do we solve this problem? Here's step by step what I would do. First, you have to solve for the total resistance. Yes, it's painful because you have to do that parallel formula in there. Once you have total resistance, you can calculate total current, right? Ohm's law, V divided by R, which also equals the current through resistor 1. Since you now have the current through resistor 1, we can calculate the voltage across resistor 1. Again, Ohm's law, V equals I times R. Since we now have that voltage, we can find the voltage. That voltage actually has nothing to do with it. We can find the voltage across our VR5 and VR6. Remember, they're the same because they're in parallel. If we multiply the total current times that parallel combination, we will find the voltage across those two. Once we have the voltage across those two, Ohm's law, right? I equals V over R. We can solve for those two currents. Now, we can calculate that voltage VR5, right? Remember that formula that we wrote back here using Kirchoff's voltage law around the outer loop? We can take and we can solve that for VR4, right? The source minus VR1 minus VR2 gives us VR4. With VR4, we can calculate the current through resistor number 4. Once we have that current, we can use Kirchoff's current law, right? So IR2 is going to be equal to IR3, and we simply take the total, subtract from IR4, and we got that current. With that, we can calculate the last two voltages. Now we have all the voltages, all the currents for this series parallel circuit. So the last thing that we normally calculate is the power. Remember, power is heat dissipated in a resistor. We calculate power, you can use any formula you want. Again, I suggest I times V, remembering to use the right I and the right V for the power of whatever particular element you're calculating from. There you go. So now you know everything there is to know about solving series parallel resistive circuits.